So I'm going to start off by reminding you again, the first midterm is Monday. It will be 30 questions, multiple choice. It will cover material through today and a little bit, which is bouncing balls, and a little bit into carousels and roller coasters. So carousels and roller coasters you'll see is the experience of acceleration. What does it feel like to be accelerating? And we'll do a little bit of that on Friday, enough of that on Friday that I'll probably ask you a question or two about it. So everything up until then. 30 multiple choice questions. Same idea I've been doing for the past 5 years. Prior to I don't know, 2013, 14, I had only one midterm. I then made it 2. So if you go back far enough, you'll find midterms that occurred actually in the middle of the semester and therefore covered more material. So anyway, look back at the old exams. Take the old exams. Again, don't look at them. It's not a learning experience so much as a memorizing. And if you see questions that seem to have nothing to do with this semester, they may be in our future or they may be something that I changed. Go far enough back and my topics began to change. Any other questions about the exam? And bring a pencil. All right. So we left off last time, or I left off talking about spring scales. Let me just briefly summarize that, and then I'll actually ask you a question just to sort of get you thinking. And I probably said it before, I'll say it again, that even if you carry away no physics from the semester into the future past maybe a year or two, if you learn some problem-solving skills, what's higher education for? It's like learning how to think and to think about problems and understand them and solve them, whether it's in politics as opposed to physics, I don't care. It's just worth learning, worth developing at least. So spring scales, the short story about spring scales is they measure weight, and they do it by supporting an object against the force of gravity. The force of gravity, of course, is the object's weight. They push up on the object just enough to support its weight so that it's at equilibrium, zero net force, and then the scale then looks at itself and says, how hard am I pushing? And it reports it to you. And that it's able to do that is kind of remarkable. It figures out how hard it's pushing up on an object. I can't do that. You can't either. I mean, you can do it. You can get it guessed. You know, this feels like a pound, or this feels like 100 pounds. You can tell a difference there, but you can't get the second digit very well. A spring scale can, because first off, by using a spring, it has this wonderful feature of a spring, which is that a spring pushes back on its parts in proportion to how far you've distorted it. So if you smush a spring 1 unit of smush, it pushes back with 1 unit of force. If you do 2 units of smush, it pushes back with 2 units of force. They're proportional. The distortion and the force are proportional. And actually, I should say that some springs are torsional. There are rotational springs too. So in any case, they push back in proportion to how far you've distorted them. And so the spring scale only has to look at the distortion of its spring. And as long as it knows that a certain distortion corresponds to a certain force, it can report to you the force. And that's what it does. So any questions about spring scales and concept? Yeah, a question just came in. I'll come back to this in a second. So the spring scale measures that distortion, reports it to you, and a crucial issue with respect to the measurement is it assumes that what it's supporting is at equilibrium. It's not accelerating. If it is accelerating, life gets complicated. So let me ask you this. I'm going to ask you a clicker question here. And here it is. Just to get you all thinking. What happens if you take your scale into an elevator and you get on the first floor of a tall building and you press the up button. You're on the first floor, you press the up button for the 100th floor, and during that initial startup process, when it goes from motionless to cruising up towards the top of the building, what does the scale read? Any questions about the question? All right, let's try it and see what you come up with. And again, you're welcome to talk about this among yourselves. It's not unanimous. It's significantly in favor of the correct answer, but not nearly unanimous. Yeah?
Is it in that instant that it starts moving upward?
Is it in the instant it starts moving upward? It's not a single instant. There's a certain startup period when you go from motionless to maximum speed. It's during that period between motionless and maximum speed. And this is a problem-solving question. It requires that you put together a couple of conceptual pieces. All right, 5, 4, 3, 2, 1. Dun, da, da. B is the correct answer. Someone want to explain why B is the correct answer? Horrifying notion to actually speak. I could do it on the yeah, Matt. Because it's accelerating. In which direction is it accelerating? Upward. What does it take for you to accelerate upward? Yeah, you need a net force upward, right? So you're not at equilibrium. You're being pushed up harder than gravity is pulling you down, so there's a net force upward on you. And the scale is what's providing that upward force that's bigger than your weight. And it tells you, I'm pushing harder than your weight. So you can try this. It was easier back in the day when scales were spring with dial because it reads instantly, whereas some of the electronic ones you get on it and da-da-da-da-da, and then it reads. So it's a little, but if you do this, if you go ride an elevator with a scale, you'll discover during that upward acceleration period, it will read heavy, more than your weight. Yeah, I don't know how you can exploit this. So an Instagram photo of you reading extra light. What would you do in order to read extra light on the scale? Accelerate downward. You want to read really light? Stick the scale to your feet and jump off the top of a building. Oh well, bad idea. Sorry. A very short building. Okay. No way. Come back to life here. Sorry about that. Anyway. Okay, so with that, I think I'll leave spring scales. And we'll go over to a different sort of mechanical world object, and that is bouncing balls. And the idea behind bouncing balls is when two things hit each other, whether it's a ball on the ground, or whether it's a ball on a bat, whether it's a ball on your leg, whether it's two balls hitting each other on a billiard table, that process has some universal aspects that you can understand and that gives you some ideas finally of how you can predict what will happen and why. And I will actually start here with a question that's got sort of an interesting result that, let's try this one. It's up there, oh. Cool. What do you think about this? If I take a basketball and a tennis ball, which I just happen to have here, and I stack them, and I drop the stack on the ground, how high is the tennis ball going to go? Any questions about the question? See what you think. The overwhelming majority of you have got the correct answer. I'll give you another 10 seconds. And I should say it's not entirely obvious. It's 5, 4, 3, 2, 1. And I can, instead of showing you your choices first, I'll show you the result first. I'll show you the choices first. I can't stand it. All right. So the majority are going for much higher. You want to see whether that's right or wrong? All right? It's a hazardous experiment. I often get hit by the ball. In principle, if this ball is very big, a lot of mass, this one's got almost no mass, and they're super bouncy, this can go 9 times as high as it started. I should, rather than just play that as a magic trick, why did that happen? It happened because the tennis ball, instead of bouncing off the floor, and it will bounce modestly well, and usually these things get old fast, so this is probably an old tennis ball, it doesn't bounce all that well, which is part of today. Instead of bouncing off the motionless floor, it's actually bouncing off the basketball as the basketball bounces itself, and so it's essentially bouncing off a rising basketball. And the basketball then bats it like a bat or like your foot and smacks it into the air. So it goes higher than it would normally bounce. So lots of the pieces that we'll talk about, cover today, all at once. Okay, so blink. Okay, bouncing balls. When a ball hits, if I drop a ball, I'll stick with a tennis ball. When I drop a ball onto a motionless, rigid surface, its energy goes from gravitational potential energy. So we're starting to use the tools that we've developed. Right now, it's gravitational potential energy that I invested by doing work, lifting it upward. When I let go, it converts its gravitational potential energy into kinetic energy, bounces, comes off with kinetic energy, and then converts its kinetic energy back into gravitational. So it's too fast. Let me go slow. I'll animate the process. I let go of the ball, and then I talk slow. Okay. It goes faster and faster and faster because it's falling, right? Accelerating downward. It reaches maximum speed at about the time it touches the table. It actually continues to speed up a little bit even as it touches the table. But it now has converted essentially all of its available gravitational potential energy into kinetic energy. It's moving at peak speed. And then something weird happens. It comes to a dead stop for a moment. Where'd the energy go? We'll come back to that. The energy that's disappeared returns, and the ball is suddenly rising off the table at peak speed. It's a new peak speed, but it's as fast as it's going to be traveling in the second half of the story. And that ball then rises to a certain height, having converted its its kinetic energy back into gravitational, right? So it starts with this much energy in the form of gravitational. Remember, gravitational potential energy is proportional to altitude. So I've invested this much altitude's worth of potential energy in it. It goes in, it rebounds, it comes back to here. It has lost a little more than half of its original energy. It had this much, it had gravitational potential energy that was proportional to this height. And it ends up with gravitational potential energy proportional to this height. So a couple of important observations are, somehow during the impact it stored the energy as some sort of potential that we can't see because it wasn't moving for one instant. And I hope you're comfortable with the idea that it actually comes to a dead stop for one instant. So the energy is all hidden. And then it rebounds, and it doesn't rebound to full height. So some of the energy that it started with, that I invested in it lifting it, is gone and never to be seen again. Where'd it go? Okay, well, the answer to the second part is it turned primarily into thermal energy. Something internal to the ball squandered part of the energy I initially invested. It's gone. Where'd it go? The ball now has more thermal energy than before. And it actually does get hotter. And I've seen kids doing the experiment of basically bouncing a ball that doesn't bounce very well many times, and then measuring its temperature, and sure enough, it's gotten hotter. So the energy gets all ground up. But during, so what really happened during the impact? It's all the actions during the impact. During the impact of the ball with this rigid surface, the floor, and make life simple by starting with a rigid surface. It can't move, it can't dent, it can't do anything except just sit there. As the ball goes into the surface, it dents, the ball dents. The ball, if you take a flash photograph of the ball at the moment when it came to motionlessness, it will have a flat, the face on it, let me stop using this ball for a second, go to a bigger ball. It will be smashed flat. There'll be a portion, say, of the basketball during that impact where it's not spherical anymore, it's been squished. You all okay with that? And the act of pushing the surface in with my finger requires work. I have to do work on it to dent that part in. So it's a little weird because if you were, instead of watching the ball hit, let's ride the ball. And as the ball is coming down and we're going with it, this surface is coming up against it. Here comes, so here we're riding the ball. And now the floor is coming up, it hits, it dents. The floor is in effect doing work on the surface, pushing it inward, denting it. Now, that point of view is messy because it involves acceleration. But the basic idea is still relatively sound, that energy that was kinetic is being invested into the surface in the form of a dent. And this ball stores it as some sort of elastic energy. Elastic potential energy. And by using that name, I'm sweeping lots of messy details under the rug. Different balls are different. Some balls are filled with air, and the energy is actually stored in the compressed air, at least to some extent. Some balls, on the other hand, are solid rubber, and it's stored then, therefore, the energy is stored in the compression of the rubber, in the denting of springy rubber. So the energy goes in during the dent, and then it comes back out as the ball undents. When the ball is deeply dented, that occurs when the floor is pushing like crazy on the bottom of the ball. And that's an upward force on the ball that's way stronger than the ball's weight. So the ball is experiencing a large upward net force during at the peak of the dent, the maximum dent. It's experiencing a large upward force, and that means it's accelerating upward dramatically. So during the bounce, let's just pick apart the bounce, let me walk you through the acceleration process. The ball is first accelerating downward. When I let go of it, it falls, and it's accelerating downward at the famous acceleration due to gravity. Then it starts to touch the table. And as it touches the table, it goes through this whole bouncing, oscillating, negotiating process that I've talked to death already, where the table and the ball begin to push harder and harder and harder on each other. And there will come a point at which the table is now pushing hard enough on the ball to support its weight. The ball will momentarily be at equilibrium. It's coming down, it's touching, it's beginning to push harder and harder on the table, and the table is pushing harder and harder on it, and there will come a moment where the table is pushing enough to support the ball. But that doesn't mean the ball is motionless. It means the ball isn't accelerating at that moment. The ball is still heading downward. So it cruises right through equilibrium, it overshoots. It goes so deeply into the table that the table now is going, you're way in my face. It pushes up like crazy, way more than the ball's weight. So in that deepest part of the dent, the ball is over-supported to the point where it's accelerating upward really fast. That causes it to come to a dead stop and then continue to pick up speed upward. And it begins to undent. And as it undents, there will come a moment when it's undented enough that the table and ball push on each other more gently, and the ball is only just supported again. Its weight is now just supported. It's at equilibrium again on the way up, but it overshoots because it was moving up when it got there. So it cruises right through the equilibrium and leaps off the table. So that's like the the total dissection of the bounce. It all happened in a real short period of time. But the ball went through that whole cycle. Accelerating downward, at equilibrium, overshooting. Accelerating, going upward, at equilibrium, overshooting, and back up into the air. You okay with that? It is what it is. I mean, it's a long story, but it is the situation. And part of the issue here is during that process of denting and storing the energy as some sort of elastic potential in the ball, and then undenting and releasing that energy, what fraction of the energy came back out? And it turns out different balls return different amounts of the bounce energy. And just give the energy a better name. The energy that gets invested into the system consisting of the ball and what it hits. Those two things hit each other. Right now the floor isn't moving, but really this bouncing story is going to involve both the ball and the floor. When they hit each other, a certain amount of energy seems to sort of disappear. It was kinetic up until this point, kinetic energy, and it vanished because everything sort of slowed to a stop. That energy that vanished is I call it the collision energy, just to give it a name. And it is a certain amount, and you could in principle measure it. And then, once the ball rebounds and comes back off the floor, a certain amount of energy reappeared as kinetic energy. How much is there? Well, that amount that reappeared, I call it the rebound energy. And the rebound energy is always, alas, less than the collision energy. The ball always squanders some energy. And it means that the energy that goes into the collision, some of it's lost and the ball comes out less. In order for the rebound energy to exceed the collision energy, it would have to find new sources of energy. So it would have to have something built into the ball that pops and that bursts forth with extra energy. What is this? Is flubber? You know, the old, my crazy professor. I don't know, the flying bicycle with, anyway, it doesn't matter. That wasn't me flying the bicycle. Rebound energy is always less than collision energy. The only exceptions to that are atoms. Atomic systems are so simple, some of them, that they actually can bounce perfectly. And the rebound energy and collision energy can be the same. But everything else, you lose some energy. And for this basketball, it's losing about half of the energy. How do I know that? Because if I start at this height with the ball, which is an investment of gravitational potential energy proportional to my height about. If I drop it, it rebounds to about half my height, which means that about half the energy reappeared and ultimately turned into gravitational potential. And it comes about because the gravitational potential is proportional to height. Hopefully you can, that's followable. So you're okay with that idea that I drop a ball, it loses half the energy and it comes back? And you know from playing sports that balls that have air in them as the energy storage medium, and that basketball is a case in point, but so is a tennis ball and they're a bunch of hollow balls that store energy in the air. You want to keep a lot of pressure in that air. It stores the energy better. As the air comes out, the ball loses its ability to bounce well. And so you can call the energy ratio, which is a ratio, which is the rebound energy divided by the collision energy, a quantity that is always less than 1, meaning the rebound energy never quite lives up to the collision energy. The smaller that rebound energy ratio, the energy ratio is, the less bouncy the ball is, the more it wastes energy. So this guy is about 50%. You know, the ratio is about half. Tennis ball here, that guy's about 40% probably. A golf ball should be about 70%. It's good, right? It's coming pretty high. So it does better. This bouncy ball, decent, not great. This bouncy ball, I want to let you guys see this, right? This bouncy ball, decent again. This bouncy ball, really, really bad. They engineer, certain rubbers have been engineered chemically and otherwise so that they have essentially no rebound at all. They are just dead. The lively and dead are language I use naturally. I hope that this would be called a lively ball. It bounces well, it stores energy well, returns it well. This ball is a dead ball. It stores energy extremely badly, doesn't return much of it at all. Almost no rebound. All the energy became thermal. Yeah, Emma? Great. Assuming that I can aim, can I stand on the table and do this so you can see it properly? This is the bouncy one. Nope, that's the dead one. Here's the lively one, right? About half the energy is coming back. This guy, about 0. And there are reasons to make rubber like this that just don't, excuse me, that just don't rebound. They soak up vibrations. It's like if you want to damp out things that are vibrating, you want to mount it on pieces of rubber like that, where you push on it, instead of like storing the energy and bouncing back from it, it just sucks the energy out and says, fine, you're gone. Okay? Well, this bouncing process and the different bounces of the different balls is important because a lot of the sports, maybe all the ball sports probably, they regulate the bounciness, the liveliness of the balls involved. Because it affects the games. And people, partly it's an issue of keeping consistent with history and records and all that stuff, and it's partly so that you don't spoil the game by making something suddenly way too easy or way too hard. So, for example, to me, sort of a classic example is the regulation of a baseball. A baseball has a regulated liveliness. If it's too bouncy, it's going to be, people will hit home runs all the time. If it's too dead, the ball will basically stick to the bat when you hit it and won't go very far. So we'll talk a bit about batting balls and so on. But to keep the game consistent, the liveliness of the ball is regulated. And for some reason, it's not regulated in terms of the energy ratio. That is, the ratio of the rebound energy to collision energy. It's regulated in terms of the outgoing speed divided by the incoming speed. When a baseball, for example, hits a rigid, solid, immovable surface, it approaches at a certain speed, how fast it's coming toward that surface. And it could be, in this case, it was, 10 miles an hour, approximately. When it came off the surface, having finished the bounce, it will come off at about 5 miles an hour. So it went from 10 to 5. Actually, let me nail it right down. From 10 to 5.5. That ratio, the outgoing speed being 5.5, to the incoming speed being 10, that ratio is 0.55. And that ratio of speeds is known as the coefficient of restitution. Big mouthful. You don't need to remember it, but it is what it's called. And a lot of sports their balls are regulated in terms of the coefficient of restitution. Divide the outgoing speed by the incoming speed, you'll get a value. The ball better be in a certain range. If it's not legal. Golf balls have a different coefficient of restitution. If you go looking through all the ball sports, they'll give you some opinions about what's allowed, what's not allowed. In the case of baseball, the coefficient of restitution really is 0.55, and there's some margin for error. Well, that means that it loses half its speed in going from almost half its speed from its approach to its rebound. How does that affect its energy? It turns out that, and I've never said this in class, it's certainly in the book and in probably my lectures, the kinetic energy that an object carries with it is proportional not to its speed, but to its speed squared. Why is this? I can say because it's in the mathematics of moving objects and what is the conserved quantity. So speed squared. So it means if you lose half your speed, you have to square that to see how much energy you lost. You actually have lost 3/4 of your energy. A ball that's coming back with only 5 miles an hour has 1/4 the energy of a ball that went in going 10 miles an hour. Is that okay? So a baseball is actually a pretty dead ball by design. It does not bounce well. It comes back to about 1/4 of its original height because of this coefficient restitution requirement. All right? The other balls have different values. So that is decent coverage of balls and bouncing balls. Anything else I want to say about this? Billiard balls are pretty high. They're pretty close to it. They try to get them the energy ratio close to 1 so they bounce really nicely. Any other balls like that? Okay. Let me, before going on to the next issue with bouncing balls, so this is bouncing balls off rigid objects. Before going to that question that came in about, can I explain situations when momentum is conserved or not conserved? So to respond to that, momentum is always conserved. Pick some isolated system. And what's isolated in this case? It means that nothing's exerting a force on it, and it's not exerting any force on anything else. That isolated system, it can have lots of parts. Whatever momentum it's got right now, it's going to keep having. Why? Because it can't, there's no way it can transfer its momentum to anything, because I told you, no forces to the outside world. It's by itself. And so the momentum inside that enclosure, that isolated world, has to stay constant. It's a fundamental to our universe. And as I mentioned last time, it has to do with the uniformity of space. That the physics here is this, and I'm juggling here. The physics here, it's all the same. There's nothing special about that location in space for me to be moving along and suddenly stop here. Why? That's not a special spot. So I just keep going. So momentum is a conserved quantity in our universe. Where momentum might change is in a not isolated system. So for example, if I'm moving across the room on incredibly slippery ice or roller skates that are just perfect and no air resistance and all that, I'm basically an isolated system. Nothing's exerting a force on me. We can worry about the up, down, and the floor, gravity, just a nuisance. Let's set it aside. I'm just coasting along. I can't change my momentum. But if someone comes up and touches me, pushes on me horizontally, or I hit the wall or any of that, now my momentum can change because I'm exerting a force on something for time, and that's how you pass along momentum. Force times time, impulse. I can do it slowly with a little force for a long time, or I can do it fast with a big force for a short time. My preference always is the long transfer with a small force because it feels better. Is that okay? All right, so bouncing balls. We've got balls bouncing off of rigid surfaces. What happens if a ball bounces off a non-rigid surface? And in reality, surfaces are all non-rigid. It's just a question of how much. If the floor were solid diamond here, which is about as hard and rigid as you can get, it's still going to dent slightly when the ball hits it. If you push on it, it's going to respond with a little bit of distortion. So what happens when the surface deforms? Well, when that happens and you look in at the collision between these two objects, they're both denting. They're exerting equal but opposite forces on one another, as Newton's third law requires. And both of them are moving a distance in the direction of that force. From the perspective of like a bug sitting there watching the bounce occur. You're staring at it here and you're going, whoa, look, they're both denting. And they're both, the ball dents up and has work done on it, and the table dents down and has work done on it. They both get a dose of that collision energy. They're sharing it now. It's not purely invested in the ball. And the relative investment has to do with who dents the most. If the surface is pretty rigid, like a wood surface is pretty rigid, now the ball may dent 50 units of distance for every one the wood dents. And this is sort of true in a wood bat hitting a conventional baseball. The wood bat barely dents, but it does dent a little. It's about a 50 to 1. Well, that means the wood bat gets about 1/50th of the collision energy. And that might matter. Where it begins to matter is surfaces, like balls, have different bounciness. There are surfaces that are very lively, that bounce nicely, and there are surfaces that don't. And an example of a surface that does, it's gone, I missed it, okay. A surface that doesn't bounce well is sand. When you dent sand, it doesn't rebound at all, it doesn't come back. So energy invested into sand during a collision of a ball and sand is gone. And so if you give the sand some of the bounce energy, you're not going to get a very good rebound. And you know this from experience. You try to bounce balls on sand. So we'll start with even, this is decently bouncy, right? Come back, right? If I try to bounce it on sand, thunk. Why did that happen? Two things happen. Two things are involved. First off, the sand is softer than the ball, and therefore gets the lion's share of the collision energy. When the sand and the ball push on each other, they push, and the sand goes denting like crazy, and the ball doesn't dent very much. So the ball doesn't get very much energy to work with. The ball does save its energy pretty nicely and does try to return it. But since most of the energy went into the sand and doesn't come back, the ball doesn't bounce very well. So this is a case of and I can go for where's the really lively ball? There they are. Not you, you're later. This guy's plenty bouncy, but not on sand. You okay? And tools for a living. This is why running on soft sand is so exhausting. Yeah, we're talking about balls bouncing, but it's the same physics as when you're running along, your soles matter. The soles of your shoe matter. The surface you're running on matter. There's some bouncing motions going on in here. The energy goes in, it gets stored, your foot comes to a stop, then your foot rebounds and comes off, it speeds back up. And you're used to having some energy reappear in the running process. So when you land your foot, the energy is sent back to you by that pair. The track surfaces, some of the modern track surfaces are themselves bouncy. They're rubber. They're rubberized. And so they store energy and they give it back to you. This is good. It helps you keep going. But if you run on something like sand, you push on it, it dents, you do work on it, which is, oh my gosh, you're giving it energy, like clearly, forced down, it moves down, lots of energy, and you don't get the energy back. So it just sucks energy out of you with every single step. The same thing's going on here. The ball hits, sucks the energy out of the ball, doesn't rebound. Is it okay? What's the alternative? The other way to go around with this ball is itself incredibly dead, right? It doesn't bounce worth anything. But if you pair it with a soft surface that is itself very lively, it stores energy well, and it's soft enough that it gets a good fraction of the collision energy when the two push on each other. It dents a lot. It gets a lot of that work done on it. You can make even this guy bounce. And an example here is just this plastic bag with air in it. It's going to dent when I drop the little ball on it, and it makes the little ball bounce. It's the world's deadest ball, and yet the bounce is decent because it's not the ball storing the energy. It's the surface storing the energy. All right? Other examples of that, people, we are, physicists, economists, mathematicians all like to simplify things to the simplest possible. The joke is, imagine a spherical cow, just to make it simple as possible, okay? Humans, you can simplify us to being a ball, a very not lively ball, very dead ball. No pun there meant. So we don't bounce well at all. If you drop us on a hard, rigid surface, such that we're all the collision energy is invested in us. We receive it, we don't store it well, we don't bounce. All right? But you can make people bounce by dropping them not on a hard, rigid, immovable surface, but one that gives, it's soft, and that's springy, stores the energy well and returns it, like a trampoline. So I'm not going to jump on a trampoline myself, but pretend this will be our person. It's just a bean bag. Actually, it's just a balloon with beans in it. We don't bounce. But if you take this guy and go into that surface, the surface does most of the denting, stores energy well. That's its reason for being, and returns the energy away, and you bounce. So people can bounce if you bounce this off the right surfaces. It's okay? Anything else? That's good. All right. Next thing to consider. So we've got now both the surface and the ball involved in the bouncing. What if the surface isn't motionless? And so this is sort of leading back to that initial demonstration I did where I dropped the stack and the ball goes off like crazy. Didn't type anything useful. It would be nice if it typed a really good paper and published it. Anyway, so that's ball bouncing off a moving surface. And a lot of ball sports have that going on. When you kick a ball, when you hit a ball with your hand, when you hit a ball with a bat, when the ball, most of those are bounces. They're bounces off moving surfaces. And how do you deal with that? So, to deal with that, let's take a look at this, at the story, and then I'll try to walk you through. Well, I'll walk you through. It's in the book, but I'll do it here, and we can talk about it if questions come up. If you bounce a ball off a surface that is motionless and stays motionless, you just see the liveliness of the ball, the collision energy, bounce energy, follow the official rules. But if the surface is moving, now the two objects are approaching each other. They both carry with them kinetic energy. The bounce occurs. You can actually end up with more energy in the ball than you started with, at the expense of energy taken out of the surface. And so the story gets complicated at how to make it as simple as possible. Let me try to walk you guys through hitting a baseball with a bat. So here is a picture from the book. And I'll modestly dim down the light. Let me take the bat out here so I can play with it. When a ball hits a rigid, immovable bat, it bounces badly. But suppose it hits a moving bat. Now we have to think much more carefully. And the story that I'll tell you, and that we'll follow, we'll have just about enough time to do this, I hope. Suppose the pitcher in baseball, presumably many or most of you know the story of baseball. It involves somebody throwing a ball down into the left in this picture, we're looking from above, and having the batter hit it as it approaches. So both the ball and the bat are moving. And for simplicity, I have them both moving at 100 kilometers per hour. It's about 60 miles an hour. Well, if the bat were motionless, the ball would go in at 100 kilometers an hour. It would rebound, according to the coefficient of restitution, at 55 kilometers per hour, and that would be the story. It would be a slow-moving ball going back. Boring. But the bat is moving, and it's moving toward the ball at 100 kilometers an hour itself. How quickly are the two objects approaching one another? What's their closing speed? You tell me. You think about yourself. What speed are they? If you're on the bat, watching the ball come toward you, how fast does the ball appear to be coming toward you? 200 kilometers an hour. Can you get that one? Is that okay? That approach speed is important. So you got it. The bat sees the ball coming toward it at 200 kilometers an hour. Similarly, the ball sees the bat coming at that speed. So, from the bat's perspective, the perspective of a bug on the bat, the ball is coming at 200 kilometers an hour towards it. It hits and it rebounds. And according to the rules of baseball, the coefficient of restitution is 0.55. The ball goes out away from the bat at 55% of the 200 kilometers an hour, which is 110 kilometers an hour. So after the impact, the ball, now this picture gives away the story, the ball is leaving the bat from the bat's perspective, from the perspective of a bug on the bat. The ball is going away at 110 kilometers an hour. You okay with that? Or questions about that one? Where the 110 came from? But let's go back and watch and be the fans sitting in the stands and looking. We see the ball, we see the bat moving at 100 kilometers an hour still towards the outfield, toward the pitcher. And we ask the bug on the bat, how fast is the ball going relative to you on the bat? And the bug says 110 kilometers an hour. To the fans, you have to add those two velocities. We see the bat moving. So the bat is moving towards the outfield. And the ball is outrunning the bat by 110 kilometers an hour. So the ball itself is moving at the bat's speed and direction of travel, plus the ball's speed and direction of travel relative to the bat. You have to add them. So it's 100 kilometers an hour for the bat, plus 110 for the ball. It's 210 kilometers per hour from the perspective of everybody in the stands. That's the fastest speed in the story, 210 kilometers an hour. That's like 130 miles an hour. Where did surprise, where did that come from? It came from the bounce off a moving object. And the fact the bounce occurred in essentially a moving frame of reference. And so you have to compensate for that in doing it. Just to put this in perspective of things that you might care about apart from just baseball, and part of the story that I'm leaving behind. Collisions between two cars. These kinds of relative motions matter. So when two cars, one of them traveling 50 kilometers an hour and one of them traveling 60, when they bump, if they bump and they were both heading in the same direction, so that one's going a little faster than the other bumps, the relative velocity is small. So you can have fender benders on the highway in your lane where you're both moving really fast, but your relative velocity is small. You're just barely overtaking the car in front of you. That little bounce, little energy, nothing much trouble. Head-on collisions, though, much worse. You can have cars can be moving the same speed, carrying the same kinetic energy, but when they approach in the same, they're going in opposite directions. Now, the speed with which they approach each other is huge. And energy, kinetic energy goes as the square of speed. So the energy goes up enormously. So the little takeaway, and it's a too short a version of the story, the little takeaway is if you're suddenly panicked on a highway, you're going to hit something. You're going to hit a car. You got a choice between hitting a car in your lane or hitting the oncoming car. Don't choose the oncoming car. The collision, the approach speed is too huge. And the collision energy is too high. Go for the car in your lane. I mean, obviously stay in control, but those are fender benders. The head-on collisions are nasty. All right, so I'll leave that and we'll come back little bits and pieces on Friday.